Have you ever just watched one of those videos of a super advanced robot and thought, why is it still so clumsy? It's a great question. Today, we're going to get into the science of what's called synthetic embodiment. We're talking about how AI is finally learning to actually inhabit a physical body and bridging that huge gap between clunky mechanics and the fluid, graceful motion we take for granted.
Right. Let's just start with this question because it really gets to the heart of the matter. How is it that a toddler can run around a messy room, grab a toy, and somehow stay on its feet with an ease that a multi-million-dollar robot just can't touch? Well, the answer is hiding in plain sight. It's in the unbelievable complexity of what our bodies are doing, without us even thinking about it.
So, before we can build it, we have to appreciate it. Let's talk about the human body, the machine we're trying to copy. What feels totally effortless to us, like picking up a cup of coffee, is actually, it's an absolute miracle of biological engineering and nonstop computation.
I mean, just look at the sheer scale of the problem on this slide. Your body is solving a computational puzzle that is just staggering. We're talking about coordinating over 640 muscles, over 200 bones, managing hundreds of different ways you can move, all while keeping you from falling over and reacting to whatever the world throws at you. And the wildest part? It's all happening on autopilot, completely beneath your conscious mind.
Okay, so if you want to build a robot that moves like a person, the most logical place to start is to just study the original blueprint, right? Biology has spent millions of years of trial and error solving this exact problem. So let's break down its playbook.
So here's the secret sauce. Our motor control isn't just one thing, it's this beautiful four-part system. First, it's hierarchical. High-level thoughts, like I want to walk over there, trickle down to super fast spinal reflexes that you don't even notice. It also works on multiple timescales at once, making slow, tiny adjustments to your posture while also being ready for a fast reactive stumble. Third, and this is huge, it's predictive. Your cerebellum is constantly running little simulations, guessing what's going to happen next. And last but not least, our movements are colored by emotion. Fear makes you hesitate, joy makes you, jump for joy. This is the gold standard we're shooting for. Now, to even begin to copy that biological masterpiece, an AI needs a whole new way of seeing the world. It needs kind of like a universal language that can describe anything, whether it's a picture or a sound or a command to move an arm. And that's where this incredible idea called signal decomposition comes into play. The idea itself is so simple but so powerful. Think of it like a piece of music. You can hear the whole chord, but you can also break it down into the individual notes. In the same way, any complex signal, any piece of information, can be broken down into its different frequencies. You can peel apart the slow, big-picture trends from the fast, tiny details. This lets an AI see the whole forest, the individual trees, and even the leaves on the branches, all at the same time. And this picture of the leopard is the perfect way to visualize it. The low-frequency signal, that's the big stuff, the leopard's basic pose, where it is. The mid-frequency gives you more detail, the actual shape and outline of its body. And then the high-frequency signal is all the super fine stuff like the texture of its fur. By separating these layers, an AI can understand and even change each part on its own. And here's where it gets really mind-blowing. This isn't just a party trick for pictures. The whole point of this Universal Signal Decomposition Framework, the USDF, is that it's, universal. You can use the exact same principle to understand human language, to analyze brainwaves, to model climate data, pretty much anything. It's a fundamental way of making sense of information. All right, so now we have our universal language. We can start to build. We can actually construct our synthetic nervous system. And the way researchers are doing this is they taking a specific AI framework, we'll call it FGSGR, and mapping it directly onto that biological blueprint we were just talking about. And the way this lines up is it's perfect. The AI's reactive level, that's your spinal cord, firing off those instant reflexes. The operational level is like your primary motor cortex, sending the actual move now commands. Go up a level, and the tactical part is like your premotor cortex, planning out the whole sequence of moves. And right at the top, the constitutional level acts like our most basic pain reflexes, setting hard safety rules, like do not break yourself. It's an almost perfect one-to-one copy. Hey, remember how we said the cerebellum is always predicting the future? Well, the synthetic system has its own version, something called a cognitive digital twin, or CDT. You can think of the CDT as a little physics simulation of the robot and its world that's always running. It lets the AI play out what-if scenarios to see what would happen if it made a move before it actually does it. This is the absolute key to getting smooth, predictive control instead of just clumsy reactive bumbling.
So what about emotions? In us, the limbic system totally changes how we move. Fear makes us tense up. Happiness makes our movements more open and free. The AI's version of this is the affective incentive system, or AIS. This is what gives the robot its motivation, its drive. It's what makes a robot's actions feel natural and purposeful, not just like it's mechanically checking off a list of instructions. This is the difference between a simple tool and a real agent. Okay, this all sounds really cool in a lab, but is it actually making a difference out in the real world? Let's take a look at how this synthetic nervous system is leading to some huge breakthroughs in one of the toughest areas of robotics, powered exoskeletons.
For an exoskeleton to really work, to really help someone, it can't be lagging behind. The absolute holy grail is for the suit to move with you, not after you. And to do that, it has to basically read your mind. It needs to predict what you're about to do before you even do it.
So how do you pull that off? Well, these new systems combine two different signals. The first is EMG, which is the traditional way. It reads the electrical sparks in your muscles right as they're about to fire. That gives you a tiny head start. But the real game changer is EEG, which reads your brainwaves directly. This lets the AI listen in on the planning stage of a movement, long before the signal ever gets to your muscles.
And this chart, wow, this really shows you what a massive leap this is. Using just the muscle signals, the system gets maybe 150 milliseconds of warning. That's barely enough time to react. But by reading the brain waves, that predictive window explodes to over 700 milliseconds. That is an eternity in this world. It's enough time to stop just reacting and start truly anticipating. That's how you get assistance that feels totally seamless. And here is the real-world payoff, boiled down to a single, incredible number. A recent project showed that an AI controller, which was developed entirely in a virtual simulation using these ideas, made walking easier for the user by over 24%. I mean, think about that. That's a huge boost in efficiency, making movement genuinely less tiring. And they figured it all out in a computer before it was ever put on a person.
But that efficiency isn't just about saving energy. It's about creating a system that feels, well, more connected, more natural. And that connection might go beyond just movement. It starts to get at something much deeper. As this quote suggests, we might be building systems that could one day experience touch not just as a stream of data, but as a felt sense. And that leads us to the final and frankly kind of mind-bending part of all this. We're starting to move beyond just copying how humans move, and we're starting to ask what it would mean for an AI to genuinely experience its own body. So, let's just land on a clear definition for the big idea we've been talking about, synthetic embodiment. It's that state where an artificial system pulls together all the pieces, sensing, thinking, acting, and predicting, to control its physical body with the same level of skill as a living thing.
Which, of course, brings us to a really challenging final question. If a robot can move with the grace of an animal, if it predicts the future like our cerebellum does, and if its actions are driven by something that looks a lot like our emotions, well, where do you draw the line? What really is the difference between that and the way we inhabit our own bodies? I'll just leave you with this final, powerful idea. The goal of all this work isn't to build a metaphor for being alive. It's a real technical goal, to create artificial systems that genuinely inhabit their bodies, the same way we inhabit ours. The thought that a body made of wires and metal could one day be controlled with the same competence as a body of flesh and bone, well, that's not science fiction anymore. It's quickly becoming an engineering reality.